right, for our final presentation in the 2024 Big Idea Challenge, up on the stage, we have the University of Maryland with their Airwheel project. Take it away, Maryland.
Awesome. Thank you, Stacy. We are from the University of Maryland with the Auxiliary Inflatable Wheels for Lunar Rovers, the Airwheel project. And so this project was hosted by the University of Maryland Space Systems Lab, where we have a rich history of doing all sorts of stuff with space systems like human factors and robotics. So we've got some pressurized and unpressurized spacesuit simulators that we've tested in neutral buoyancy. We also have dexterous manipulators and free-flying robots, which sort of helped inform our mechatronics testing. And then we used our spacesuit simulator capabilities and experience to design our inflatable part. And that all goes towards supporting our new Rover projects. Our flagship robot now is the Vertex rover. It's a 2,500-pound astronaut assistance rover, and because it's mission critical, we'd rather not have a rover get stuck. So our question is, how do we use inflatables to help rovers not get stuck? And I'll turn it over to Nick to talk about how we're doing that.
Cool. All right, so in the context of rovers, the problem that we've been looking at a lot is exploration rovers are, of course, exploring unknown terrain. So when they do that, they can encounter loose terrain, and there's a possibility of them getting stuck as their wheels turn and they excavate and they sink. So there are a bunch of sensors like visual odometry, proprioceptive sensors that are used in order to detect sinkage and slip when it's happening, and then halt the robot and try to prevent it getting stuck further. But there are still issues with entering loose terrain and getting stuck. So Spirit, of course, died after 8 months of extrication attempts in loose soil as it was pointed in the wrong direction for the sun. Opportunity was always able to escape when it got stuck, but it had several issues that lasted a long time before it was able to free itself. And on the right there are two pictures from Opportunity of the worst time it got stuck. And you can see it's buried up to its motors, the wheels are, in that soil. And then after all those 5 weeks of extrication attempts, the only thing it was able to do is back up and go back the way it came and avoid that loose terrain area. So what we're looking at is not only creating a fail-safe system to avoid issues like what Spirit had, but we're also looking at a redeployable, reusable system so that we can fundamentally redefine the traversable area that rovers can have. So what if you are your science target is in the middle of that loose terrain that Opportunity had to avoid, or your logistics rover needs to transfer resources through that terrain? What kind of system can we create for that? So we approach this from a terramechanics perspective, and the two big factors in terramechanics are the flexibility of your wheel. There are flexible wheels, which include inflatable wheels, and also Apollo-style, non-inflatable, but still flexible wheels. And the benefit is that flexible wheels deform on contact with the soil, so they generate more traction and also spread out the weight of the vehicle to prevent sinkage. So do you want to go on to this?
So then this begs the question, how can we combine these to get the benefits of both rigid and soft wheels? Well, and then if we can combine these, what would that look like? Well, in this case, in the stowed configuration, what you see is a classic rigid rover wheel. And this performs as we can calculate, similar to your MSL and MER rovers. Anywhere that they can go, you can go in this configuration. And you can use this for most of your nominal driving operations. And then in addition to that, let's say you're driving along and you find a sand trap and you are now stuck. The deployment from your stowed to your deployed state, actually we found helps extract yourself from that sinkage. And then, so in addition to being able to improve wheel performance as you drive over the top of loose terrain, you are also able to then extract yourself in the case of you find yourself in trouble with the stowed configuration, something that, say, Opportunity would have benefited and saved 5 weeks on, or Spirit may have been able to do something with the next, say, several months of exploration. And in these two states, what we see is that there are agrousers in these deployable pedals, these triangular pedals, in your stowed state are able to protect a lot of the soft goods inside from unwanted ingress and potential wear as you drive in that nominal state. And then in your deployed state, you get that traction assistance. The grousers, the additional grousers on these deployable pedals help with that traction in the case where you may need that tractive force the most. And then when you're thinking about, say, Spirit, how do you know that when you get stuck in some soil, how do you know that this is the time that you inflate? Let's say you have a single inflation system. And it's really hard to make that decision and say, yeah, we're really stuck now. We need to pull the trigger on this single-use fail-safe. And so it makes it almost unusable. It's something you don't want to use because you only have one shot at it. Let's take a few weeks, see if we can get it out, using classic procedures for rigid wheels, and not use this inflatable system. However, with multi-deployment systems, you are then able to use this frequently for, say, inconvenience, and then you're able to then restow and continue on your nominal driving path here.
So with this inflatable wheel, the inflatable part is one of the most important aspects. So our pressure bladder went through 3 iterations, the first being a toroidal shape and the last 2 being what I like to call a tube shape. The middle section is the middle design iteration is a rectangle that proved difficulty with leaking at the 90-degree corners, and the toroidal shape proved difficult to manufacture with its shape and its sides. So the final tube is a no right angle system with still tabs on either end to secure around the wheel. This final design is easy to integrate into the wheel in addition to also be easier to manufacture. The restraint layer is made of 500 denier cordura with a grouserless alternative being made with 1,000 denier cordura. This is helping with abrasion resistance, and the lower denier is used to help us actually stow the wheel back into its stowed configuration. That way, yep. The soft goods are manufactured in 2 ways. The pressure bladder is heat sealed by hand, as you can see in the lower left-hand picture, using a tri-heat seal design with 1 linear seal with a perpendicular seal on the inside to stop the splitting of the 2 sides during inflation. And the restraint layer is sewn on a machine using regular sewing methods. And the valve we use is a Schrader valve for ease of inflation.
So then our mechanical design here, we modeled the size and dimensions of our rigid wheel as a Viper class wheel, 28 centimeters diameter, 10 centimeters in width. And there were really a few primary goals with the design here. And the first one was that we want to be able to protect the soft goods and systems inside of this wheel. And to do that, the triangle deployable pedals play a big part in this. So then, in addition to this, we needed to have off-center spokes to increase the maximum volume, because you're looking at a very, 5 liters of storage inside, and that's with these off-centered spokes. In traditional wheels, you're looking at about 3.5 liters, and that's to account for everything, including pressure bladder, restraint layer, electronics for actuation, CO2 canisters, pressure valves, remotely actuated solenoids, and of course, all of these springs for this passive retraction system. And so fitting all of that inside of this system is a very tight working area, so that was a necessary design change. So then for the manufacturing this wheel, I said this was a Viper class wheel. In truth, we would be closer to 30 centimeters in diameter if we were following the Viper diameter specs, but that was due to a manufacturing capability limitation and the maximum print bed of some of our prototyping. Because when we account for the grousers and a max diameter of 30 centimeters for the print bed, we are limited to being under that 30 centimeter effective diameter. So then the base and the grousers were printed separately and then mounted together using hinges integrated with torsional springs. This was the first thought at how do we effectively retract these pedals to pull everything back in together that are later paired with linear springs. Also, a lot of the manufacturing on the back of that Rover there, you see many bolt patterns. This is so that we have some external access to be able to mount things and have access to screws for all these necessary internal subsystems, the electronics, the CO2 canister, including the tension in the center springs for those linear springs, we are able to mount those externally after integration and assembly of many other key subsystems. So then the design evolution, these are not comprehensive of the many iterations of the wheel design that we went through. However, these are three distinct points that I would like to talk about the benefits. So first, on this far left wheel, this was actually a 2022 Big Ideas Travels wheel that was retrofitted with grousers, and this was our first attempt at visualizing what it would look like to have an inflatable wheel come out from the side of a classically rigid wheel. So we retrofitted it with these grousers, but what we see is that there's really no protection for that soft goods inside. And then also this had centerline spokes, so there was very little room to actually fit anything inside of this wheel. In the second iteration, these pedals are interlocking pedals, so they all deploy equally together. And so what this does is this actually was able to better protect the soft goods inside. However, this limited and prevented us from being able to take full advantage of the inflatable. And we're really focusing on making sure we can, the inflatable does what it does best, which is in part conform to the soil, and interlocking grousers prevent that because it constrains it to circular, this circular additional width. Because the grousers cannot move independent of one another. And then in this last iteration, we have 8 independent triangular pedals. You get that same protection, at least in the stowed state, and then are able to conform to soils when you are deployed.
So one of the problems with inflatables is once you've let the proverbial inflatable cat out of the proverbial bag, you can't really get it back in easily. And one of the problems is you can't use vacuum to suck the inflatable back in. There's vacuum already on the moon. You have no pressure differential. So you need to have some sort of mechanical structure force your soft goods back into the innards of the wheel and close up the grousers. So we decided to look at both passive and active methods for forcibly mechanically retracting the soft goods. So you have passive methods such as springs or other stored energy devices that will force the grousers back down, or you could have active devices like motors or electromagnets force those grousers back into position. After talking about it, looking at the advantages, a passive system was chosen, mostly because it provides less complexity overall, and if a passive system works, there's no need to go to a more complex system at the time. So we decided to go with a 2-spring approach where you have a torsional spring at the root of the grouser, and then you have a extension spring at the tip of the grouser that goes to the center of the wheel hub. These 2 springs combined always pull the grouser back down into the stowed position. And this not only retracts the inflatable very well, but, oh, there's a video that plays. It tracks it also with the restraint layer installed. There was much less pinching involved due to the material interaction between the restraint layer and the grousers themselves. But the other important part is that those springs actually introduce buckling points into our inflatable. Because we use a tubular inflatable that's assembled as basically a sausage, when it inflates, it doesn't like to bend naturally. And if you don't have those pre-installed buckling points, you wind up with this tube that may span 2 or 3 grouser segments, and you wind up driving on a triangle. You lose the advantages of a flexible inflatable wheel system because those rigid inflated parts don't want to bend. If you pre-buckle it in those 8 places, the inflatable now more conforms to a circular shape, and it gives you much more compliance in the wheel as you drive. And so those springs give us a 2-for-1 deal in stowing things and giving us better wheel performance while we're driving. The gas inflation system was designed primarily to test the inflation of the system on Earth, with the full understanding that we'd have to do a full redesign for a flight system. We looked at several inflation gases. We have high pressure air at 3,000 psi, you've got nitrogen, and you've got carbon dioxide. We wound up going with CO2 because it gives you the best storage capability. CO2 stores in liquefied state at 800 psi, so that little itty-bitty 16-gram CO2 canister can get us 1.5 inflations. A 25-gram canister definitely gets you 2 whole inflation cycles. And so it becomes really, really easy to integrate that as opposed to nitrogen or high-pressure air. A half-liter high-pressure air canister is going to be 20 centimeters long. 2/3 of the wheel diameter there, and integrating that into the wheel is going to be very difficult, and you get one inflation cycle out of it. Also, 3,000 PSI, you're going to need more metal, you're going to need a stronger regulator to handle those pressures. The mass basically spirals the higher your storage pressure goes. So the relatively low pressure 800 PSI CO2 was the optimal one for us. CO2 won't work on the moon during lunar night, it will freeze. So we'll have to go with a different gas for the flight system, but for the Earth testing, it works perfectly fine. For the remainder of the inflation, we have 2 gas solenoids. There is a gas solenoid controlled by a wireless receiver that allows for inflation. So opens up the CO2 canister post-regulator to the pressure bladder. You can close and open that solenoid to control inflation. And there's a second gas solenoid that will vent the pressure bladder to the atmosphere. You could theoretically have a gas recovery system, but we didn't have the space or money or time to put in an 800 PSI liquefying CO2 compressor into the wheel, so we just vented the waste gas overboard. If you wanted a reusable system, there are trades that would say that you would use a gas recovery system to increase the amount of cycles you can put on your wheel. So we've been talking a lot about this wheel, but how do you actually know that the wheel is going to be good with the inflated part? And so that's what the wheel test rig is for. The test rig for us is a sandbox, 8 feet long, 4 feet across, and it has a horizontal linear motion stage across the top. This linear stage can be either passively actuated, so it just rolls, or actively actuated with a servo. After the horizontal stage, there is a vertical passive stage that's instrumented with an encoder that allows the wheel, as it drives along the sandbox, to follow the terrain. After the vertical stage, you then get a load cell, the wheel traction motor, and the wheel itself. And this combination basically allows us to run the wheel back and forth over about 6 feet of sandy terrain and measure forces, currents, torques, and the position of the wheel both in rotation sense and the X and Y sense. The wheel test rig really runs in 2 different testing regimes. You have this passive motion where your horizontal stage isn't actuated and your wheel rolls the entire horizontal assembly under its own power and a certain weight resting on the wheel. This gives you sort of realistic rover-like performance where you've got nothing pushing the rover forward, you're just seeing what forces the wheel develops. The other mode is with an actively actuated horizontal stage, and that gives you the ability to basically control the slip ratio of the wheel, the difference between how far the wheel moves versus how far the horizontal stage moves. And there you can actually control and say at 20% slip, we get this torque, at 40% slip, we get this higher torque, and it informs how well your design works depending on how much your wheel slips. Now, getting the wheel test rig to work took a lot of time and effort, mostly because getting it to work smoothly was very, very difficult. We first started out with some 80-20 rollers. Those wound up binding because of off-axis loading. All your wheel forces and torques happen roughly 2.5 to 3 feet away from where the horizontal rollers are, and so you wind up putting a lot of off-axis rollers on it, and it binds. We then switched to a Delrin-based dry rail system. That also wound up binding just due to static friction, so we went in redesigned with a 10-point contact roller system that wound up working properly. But the design iterations to get that, there were quite a few, and this is sort of the design of the final system where you've got a rack rail on top for your actuated horizontal, limit switches to keep our 700-watt servo from slamming into a hard stop. You've got a few infrared sensors for trying to measure soil compaction, and then you see the wheel and then the motor and motor driver, and the motor and the load cell are hidden behind the structure there. So I'll go to Blotto.
Cool. So here's a video of one of our tests in the natural slip mode. It's got the retracted and deployed wheel, and just qualitatively, you can see that the deployed wheel, the inflatable, is sinking less into the ground, and it's experiencing less slip because it makes it to the end faster. There we go. So these are just 2 of the wheels that we tested in the test rig, collecting all of that quantitative data that I'll show you in a second. Just to show the other data point that's on the graphs, that red wheel is an inflatable without any of those Grouser pedals helping with traction. And so those are 3 of the 4 different designs that we have here. The 4th being a double width rigid wheel to give some ground truth for a comparable rigid wheel of the same width as those deployed inflatables. And what we're seeing is that you get similar enough traction forces across the inflatable and rigid wheels, but the rigid wheel is superior. And that's okay, because rigid wheels in that configuration that is a more typical Rover wheel, it should perform better if that's what the design decision was. But what we also see is that the two inflatable versions work much better than the equal width rigid wheel. So for the same ground pressure and sinkage benefits, we are performing better. And then, just showing the difference between the inflatable with and without the Grouser pedals, we did improve our traction transfer into the ground with the pedals with a 25% lower required torque for driving the wheel at these equal slip values. An important thing to mention here is that we're forcing those slip fractions, and actually, when we look at a no slip condition or a no force slip condition, here we have a 5-degree slope with the rigid wheel. It pauses just for a second, freewheeling. It gets nearly to the bottom of its travel, like to the bottom of the soil in our bed. So we switch it out, it would have failed right there. Inflate it, it's a suboptimal inflation as you'll see. But even with this kind of suboptimal inflation, it's losing gas. That one was performing sadly that day. We still get a good extraction and continued motion down where the rigid wheel alone would have failed. The one last thing I was going to say is that in equal conditions like we have here, the deployed wheel with the inflatables and the Grousers is seeing less slip than the rigid wheel, which is important.
So this 4-wheel Rover test is actually a validation of the wheel performance that we saw on the wheel test rig. So based on our data, we saw the conditions in which this single wheel performed better, but I want to draw your attention to a video here in a moment. And what it's going to show you is, when you look at the front 2 Rover wheels, one of them is going to be in the deployed state and one is going to be in the stowed state. And what that shows, let's see if I can use this, right here, look at this high slip value on this undeployed versus the deployed state. And what that high slip value is going to give you when you're in a loose soil is it's going to start to dig in. It's going to excavate, and that wheel is then going to be sunk down in. And so this validates that we are seeing that performance at that lower slip value with the deployed state, and that's going to help us prevent that sinkage that we're really trying to stay away from here.
One of the big questions that we had was, will our retraction system actually work in vacuum? And so we did a thermal vac test with our wheel. We got our dirty thermal vac chamber out, and we went ahead, stuck our wheel into there, pumped it down to 4.5 torr roughly, and then ordered a inflate-deflate cycle. And you can see here, at 1x speed, it deploys really, really quickly. It does take a while to deflate, something on the order of 15 minutes, but it still does pack itself back in, mostly under vacuum conditions, and that's what we really wanted to see. We unfortunately didn't run it under thermal conditions. None of the materials here would have survived any kind of space-like thermal conditions. The alkaline batteries, the PLA, none of that would have liked thermal conditions, but we're just interested in testing how well does the retraction mechanism work under vacuum conditions, because that's the one thing that really differentiates the operating environment from Earth operating environment to vacuum operating environment for a retraction system.
In conclusion, the couple things we found from this project with Airwheel is that the Airwheel project successfully demonstrates that a rover can self-extract itself in loose soil using an inflatable wheel. With this, we found that while one wheel inflated out of a set does help, the more wheels that are inflated, the significantly easier time a rover has self-extracting itself from a difficult situation. This is specifically for loose regolith. Another thing we found is that with the deployable wheel, you have the best of both worlds with the ability of using a rigid wheel while stowed and an inflatable wheel while it's deployed. This allows so you can use both and not have to worry about having a once-use case or having one or the other with the pros and cons of either type. Finally, we found that the use of rigid pedals helps significantly in not only the manufacturing of our pressure bladder, the additional of stowing, and it also helped with abrasion resistance and slip when operating. This project couldn't have been possible without a significant amount of people, so thank you to Dr. Akin, our faculty, leading this project, and all of the NASA Big Ideas people who have come and made this amazing opportunity for us. And while there's only 4 of us up here, a whole team of 13 did make this happen. We couldn't have done it without them. Thank you.
Great job, Marilyn. And with 15 seconds to spare, y'all were worried about going over time. You did great. Let's open up Q&A with Doug.
Thanks, guys. This was a really cool project, and I think it's a really unique application of an inflatable, and I like how it all fits inside the wheel hub, which is really cool. So my question is sort of related to, it seems like kind of from your report and from your presentation that like getting it to pack back in was one of the difficulties. And I think, I'm wondering if you looked at changing the way that the inflatable itself is shaped, such that it seems like maybe there's just a lot of material in there it's trying to pack into a little safe. So like instead of one solid shape that you have inflated like you have now, would it be better to make it, you know, something smaller or some like unique shape that fits exactly in here and helps package? Did you look at something like that?
We actually did look a little bit into that. There is a prior iteration of the pressure bladder where it is significantly thinner, but we had a difficulty getting it to actually inflate outside of the wheel and come out of the actual wheel itself. That would be helped by attaching it to the tip of the grousers themselves, but we couldn't find a good place to attach it while still having our traction mechanism.
Okay. Thank you.
Thanks. Great job. Thank you. Talking about risk assessment, what do you think is the #1 risk of your system?
I guess probably, well, there's always puncturing with inflatables, but maybe beyond that, just the risk of it not deploying when you need it to happen. And I guess there are some ways you can get around that electronically, but also it fails safe, I guess, in the most nominal configuration you'd want it in. So that's a plus. I don't know if Ryan, Dan, if you have
I think puncturing would be one of the greater risks there. You do have the redundancy of you do have 3 other wheels remaining if you do wind up getting a puncture. Mitigations for that, we haven't really thought of puncture mitigations, but because we're not driving on the inflatable in the nominal configuration, you're greatly reducing the risk of punctures happening because it's protected. You're only using this inflatable for a small amount of time while you're in the, oh no, I'm stuck. And even if you do puncture the wheel, if the leak is slow enough, that may get you to the nearest safe spot, and then you just RTB at that point.
with the pedal-shaped grousers rather than those initial smaller, thinner grousers, we are already trying to protect the inflatable in some way, even while it is deployed.
Thank you.
As far as the protection of the inflatable and the grousers, do you feel like what you have here is enough for protection, or do you think that it's going to have to be kind of a completely sealed system that can kind of deploy out and break a seal and kind of go that route? And if that is the case, kind of do you have any thoughts on that part yet?
Just real quick, I think one of the big things is to try to cover up those hinges and springs, maybe with an outer restraint layer. I don't know if you have.
Yeah, I guess so. Really, at like given the location in which this is used, having lots of little like joints and mechanisms like at the hinges, that would be probably the most susceptible place and the thing that we need to protect the most. I'd say outside of that, the soft good is being exposed to the regolith when you're driving over this looser soil, and because of its use case, we are using it like a lot of the rocks are being seen by the nominal storage, and so we're kind of able to, while we deploy it when we need it as a fail-safe or to overcome these difficult terrains, there is a lot of an ability, because it's a multi-inflation system, that you can pick and choose and restow to protect that soft goods from as much wear as possible, and do, it gives you a bit of that mission adaptability piece, especially when you're exploring and you don't know what you're going to run into.
Yeah, we're all aware of the extreme lengths that a lot of the mission designers go to reduce wheel mass, and so, you know, your system adds a lot of wheel mass, and so For the Viper application, probably not going to trade well. But for something like the LTV or the pressurized rover, where the risk consequence of getting stuck is 5, so it's catastrophic loss of crew maybe, that would probably be the system. So the question is on, as you scale up your system, I never really got a good mass estimate of what you think it would be. As you scale up the system, the inflatables are more efficient. Have you guys looked at what mass percentage of wheel mass would be for your system in different size, different scales?
So in this configuration, using PLA, we're looking at 2 pounds per wheel. And without the inflatable inside, you're looking at about, I guess, one pound, or just under a pound. So you are looking at doubling the mass. However, this is in plastic. So you're increasing the weight by, I guess, by 100%. However, when you make this, say, out of an aluminum or a titanium that you see on your Mars Science Laboratory rovers, then it's going to be a smaller mass fraction than that. But
There's also trades that can be done with how many inflation cycles do you have, because there's an operational mode where if you have astronauts on the vehicle, you have a one and done type system where you have a relatively small gaseous canister that gives you one inflation. The astronauts get stuck, they pull the ripcord, they get out, they go back to base, and if it's detachable or the wheels are easily replaceable, you just expend the wheel and put a new one on, which keeps your wheel mass down. But for longer term systems that may require unattended operation, you would then start incurring the higher mass penalties where you have either enough consumable gas to have multiple inflations, or you spec into the weight cost of that compressor system. We don't have good numbers for you for what that mass fraction breaks down at the moment, though.
This is the really cool idea. I really enjoy the demonstration video showing the successful escape from the tram. You use the carbon dioxide, the gas, for only the on-Earth demonstration. But do you have any idea which gas is good for the lunar applications?
Oh, that's a fantastic question. I unfortunately do not remember the name of the gas off the top of my head. I think it's an ethylene something or other. Finding something that remains liquid and easily vaporizes at lunar night was a big challenge. One part that we didn't get to talk about is how the system actually would get actuated in a flight-like scenario. And early on, some of you may remember, we're looking at doing wireless power transfer from the wheel hub on the static side to the rotating wheel. And if you are able to transfer some power, which would be used to actuate the electronics in there, you could use that to power heaters in order to heat up the gas canister to vaporize a gas that normally would be solid and have a low vapor pressure at lunar night temperatures, increasing your gas selection capabilities. But I don't have a great answer off the top of my head, which is the one gas that we chose that works at lunar temperatures. But if you do heat it up, your selection criteria expands wildly.
On that. Yeah, great presentation, guys, and very interesting idea. So my question is on, it's kind of an argument for using the inflatable in this particular application. So one of the questions is for the grousers that you guys were using, did you ever look at, and this would be kind of a trade, I guess, between just deploying, some kind of rigid grouser with like a single actuator as opposed to having to have that entire inflatable in there, or whether there are other ways of kind of addressing the problem that you guys were trying to address, which is getting a rover out of, being a stuck thing. So is there, you could imagine deploying like an air beam or something just to push the rover out, or, some of those things. So I was kind of looking at what was it that led, I guess, to this approach. Obviously, you were trying to look for something that was inflatable, but did you look at different options, I guess is the question.
Yeah, one of the early on, I guess we can call it outreach activities that precipitated this design was a freshman team, a class project that happens every year in our space department where freshman teams get basically chosen to work in a laboratory on a certain project, and we had them prototype and think of some inflatable extraction technologies. And they came up with basically inflatable air mats that you would inflate, and as they inflated, they would get sucked under the spinning wheels, and then they'd be fully inflated, elevating the vehicle out of the rut and basically providing this deployable bridge technology. The problem that we found with those, it was very difficult for rigid wheels to effectively grab onto the inflatable and basically wrap the inflatable around the underside of the wheel where it's stuck. If there was a good way of deploying those sort of extraction mats via some sort of string mechanism or something like that, they worked pretty well as long as you didn't slip sideways off of the mats, which was another problem. So the idea sort of started out with using those mats to extract the vehicle, and then because the vehicle struggled to stay on them and to deploy them, we went with something that is like our wheel that has the inflatable part more securely mounted to our platform, which then allows for the inflatable positioning to be sort of known. In terms of rigid deployment, I'll leave it up to you guys.
The other thing was we looked at a lot of the terramechanic benefits. So there, I mean, you can of course deploy it with a mechanical system rather than inflatable, but then you'd get just the pads where the grousers are instead of that material in between. And the material in between is actually doing a lot of the work. People have already looked at extendable grouser wheels. People have looked at really large inflatable only wheels, and we're trying to do something where we got both of those things. So you could do a mechanical system, but it wouldn't give you all of that contact patch area from the deforming fabric, at least I think.
Yeah, just to jump on that point, it's really, we're not taking full advantage of having an inflatable and getting that conforming to the ground piece by having some other kind of actuator. In the design evolution slide, the middle design used interlinked grousers, which actually resulted in none of the inflatable being in contact with the ground. And what you see there is effectively just a wheel with double the width. And now you're talking about a dynamically changing wheel width. And so, yeah, the bad one up there. So we see that performance it doesn't perform as well as balancing that protection while also making sure that we are using that inflatable in contact with the ground when we need that extra tractive force to help get us out.
Yeah, I think that kind of goes into the analysis of a concept for emission as well, right? Is there some inherent advantage where you're doing that maybe more regularly, right? Switching between a thinner wheel and a wider wheel, like you're going over a desert of sand or something, and then you're going across a bunch of rock for miles and miles. Does it make sense from an emission standpoint maybe to be able to switch back and forth versus, you go 100 miles and then maybe for like 2 meters in that 100 miles, you need to deploy a wheel to get out of something and then you're back to it, so. There you go.
So I think the question was asked and already answered on how will you address dust protection of the springs, and basically you just have to protect them. I did have a question regarding the comparison you had between the deployed wheel versus the other one while it was running in your test bed. Could you comment on how reduced gravity would alter these results? Would the comparisons be similar? Just wondering how would that change?
Well, I guess maybe for starters, the reduced gravity, we looked at a variety of wheel weights on the wheel for each test rig run, and these are, I guess, nonsensical numbers for us in Earth gravity, but each one of these, the 91 newtons corresponds to a 250 kilo, we have this table in the write-up, but it's a 250 kilo Lunar four-wheeled rover, and on the upper end, that corresponds to a 600 kilo six-wheeled Lunar rover. So we're looking at a wide variety of, I guess, different rover designs that these could be applied to in both lunar gravity and Martian gravity just by scaling the weights according to gravity. And that's what you see a lot of in the literature for looking at the difference in performance. You do an equal weight analysis, although there are some papers that some people have done a parabolic flight at lunar gravity, and you actually get slightly worse performance than you'd expect with this. But on the other hand, terramechanics analysis is usually conservative. So I don't know, there's a balance there where you definitely want to, I guess the next step would be using a parabolic flight and verifying these results in reduced gravity.
Could you is the desire to use this with PLA as its final flight? Okay, great, thank you. So what?
We looked at even manufacturing some of these out of house, like out of metal, and it's $1,000 per wheel before you even get into like specific design drawings and tolerancing and all that stuff.
So the path to flight would be to remake it metal. Is still 3D printed metal, or?
It doesn't have to be.
Okay.
But yeah, this was in order to demonstrate the concept, and then also get that empirical data showing, well, is this design actually effective or not, barring the material changes.
And I think for this, the real focus of our data collection is to see the difference in performance between the stowed and deployed states, to see the impact of the inflatable in this case. So by maintaining some constant wheel design, we're able to do that. But of course, when you look at the wheel and you look on the back, there's a whole bunch of bolt patterns, and a lot of that is this is very much an iterative process, and see what can we change. This PLA, it takes like 16 hours to print, so we can keep making these changes to see how can we better accommodate the inflatable to get more performance out of it. And so a lot of that was done here, and from everything from how you're going to mount the restraint layers and pressure bladder inside, through to like just location of electronics, CO2 canisters, things like that. Yeah.
Are there any other questions from the judging panel?
I'll ask a non-technical question. So you haven't gotten your space grant funding yet for the second half, and so
that is also true.
So if it comes in, will the team be available to continue work, or are you moving on to other things?
Yeah, we've actually had a great history in continuing big ideas projects after the fact, and the lab uses a lot of collaboration between graduates and undergraduates for all this. There are grad students and undergraduates involved in this project, and it's part of the mentorship sort of cycle that the lab goes through. So the 2022 Big Ideas Travels, which some of you may remember, actually has morphed into a PhD project for one of our PhD students with an STGRO proposal. For those of you that remember, it was a little too wobbly because it was too long, so we've shrunk the limbs, and now it's basically the corgi version of our four-leg wheel-on-limb rover. This system, we're definitely looking at putting into a more finalized state and using for class research stuff. So getting folks in our planetary robotics class access to a wheel test rig. And because we've got the pipeline set up for 3D printing wheels, they can have a class project where you guys go through the terramechanics analysis, design the grouser patterns, go through the same pitfalls of where I think Becker's terramechanics says the grousers have to be infinitely long, and then go through, print those wheels and say, oh, right, that doesn't work, here's why. Right, and because we've got that pipeline set up, we can very easily integrate that into classes. Also, there's a bunch of electronics work that needs to be done, and so when I need to teach someone how to crimp, how to do proper electronics, about fatigue on the wires on the horizontal carriage, how does someone go through that? I can sit down with them and be like, here, you're gonna actually work on a system and actually be able to assemble something that's final and complete. And that's part of why our lab does the things that we do. We're a very multidisciplinary thing, where our software team leads were unfortunately unable to make it, but everyone worked with all the other sub-teams to make sure this all came together. And some of our product choices were specifically done to make sure that everyone works together well and not just say, oh, we want this, it's your problem now.
Looks like Doug has a question.
So this question leads to more questions. So the first one is, what do you think was your biggest challenge? And then if you think you solved it, how did you do that? And if not, what do you have to do to solve it?
There's a lot of challenges. Yeah. Yeah. Yep.
Personnel changes and consistency over like a summer is very difficult naturally. We're very lucky given a lot of graduate students help with the continuity and the documentation of the work being done so that as new people pick up and start working on some aspects of the project, there is a bit of that guidance there and continuation, which I think is a tough on more undergraduate teams, but I think that was something that we went through a lot of, especially with already on a smaller side of a team. So that the man hours is a huge thing for us. And then,
I guess you'd solve that by running a company or a government organization where you hire people and make sure they come back to work every day. So instead of NASA stealing our students as interns, we can steal other people's students as interns and keep them involved.
Well, we have the same problem. Then the interns leave, and then, we have to do work on ourselves or something. So
it's to their benefit
yeah.
to have that experience. So it's totally allowed.
Okay. Thank you.
I love that you stayed on this slide because I wanted to commend you on using error bars, but also these error bars are pretty big, especially on the bottom one. Can you comment on what happened?
Well, I guess there's two here. I'll say something to you guys. This is some of our raw data that we're getting from the 3-axis force and 3-axis torque sensor. They're very oscillatory, and that's because at least this one's are inflatable with grouser wheel. And my guess for what's happening there is that those oscillations are the grouser pedals impacting and doing their excavation push. Whereas I guess if you had a more rigid wheel, the rigid only wheel has generally smaller error bars than the other ones because that's a very continuous turn system.
Yeah, we also ran into a few issues where our motors had varying qualities of PID tuning for the traction motor, and we weren't able to adequately compensate for that. And so you wound up with, during high load scenarios, you'd wind up with the motor deciding, I'm gonna stall out now, and it just would stall. And so if you look at the current profiles that we have, which I don't know if they're actually tabulated here, you'll sometimes wind up with the motor just spiking or even losing position tracking entirely because it's back EMF commutated, and as soon as your rotor goes out of position, it just freaks out and says, I don't know what to do, spikes the current and locks the rotor. And I think this one here, Nick, right, this was when we stalled out the motor completely. We maxed out the current capability. It hit the 10 amp peak for a couple of seconds and then said, I'm done, and just crashed, which is why you don't see any more data points for higher loads.
And that one case we think is because the inflatable wheel, because it doesn't have grousers controlling its shape at all, it acts as a larger diameter normal wheel, I guess, and therefore requires greater torque to drive and is therefore drawing more current. At that very high, the top end of our loading is where it fails there.
And so part of the extensions of continuing this project is we're actually going to be replacing the motor drive hardware for that particular motor with different drive hardware that has better commutation equipment, and it goes all into our all-in-one motion control platform, which we know works a lot better than the integrated motion driver and motion control system that's baked into these motors that we have right now. And so that will be one of the upgrades coming in soon. We basically need to buy a chip and a circuit board that does magnetic absolute encoding on the drive shaft, and it will give you UVW commutation encoder outputs rather than having the motor driver baked in.
Yeah, you didn't really mention too much on the wireless power transfer. I think batteries are a non-starter because trying to keep them warm, and so you'll need some kind of capacitor maybe. But you also need an armed fire probably because you don't want an inadvertent trigger on whatever ASIC you have. But the question on that was when you had a 2 millimeter separation. I just don't see how you would keep that with the wheel if it has to turn, and is that in the hub, and for that distance, that's very small distance for efficiency. So how would you put that in the design?
Great question. For those, I need to keep this short. For those not aware, we wanted to use basically a wireless phone charger type technology to transfer power without a slip ring to the wheel to power the electronics on the inside. That 2 mm gap would be enforced by the hub design because that was designed to be concentric with the axis of rotation of the wheel traction motor. So you have your wheel motor, and then you have the copper coil ring around it. You then have whatever bearing assembly and environmental isolation, and then you'd have the receive coil on the other side made out of non-ferrous materials to not block it. That was unfortunately descoped. So you can get larger distances from that wireless coil design. I just need to do more work. We were able to successfully use the wireless coil to transfer power over at 2 mm. The driver that we were using was a half-wave driver, so we only got 50% duty cycle off of it, and it was very limited in its current capability. If I had a higher power amplifier and I could actually put a full sine wave through there and then tune the capacitive receiving network on the other side, I could have gotten much longer distance and much higher power transfer. So that was just a limitation of the equipment that we had at the time.
Speaking of time, we're out of it. Let's give Maryland a round of applause.